So, now we saw before that digital communication system has a very simple model like this. This is the continuous time model that I am showing here once again with S of t, N of t and R of t. Now, what are the performance metrics or the important metrics that you have to focus on in a digital communication system? There are two important metrics. The first metric is signal to noise ratio. Okay. SNR is an important metric, signal to noise ratio. It is a very important metric. So, this is defined as signal power divided by noise power. Okay. So, this S of t is the transmitted signal. It will have a certain power. Okay. Power is defined for signals in a certain way. You can take the square integral of the signal and divide by the time, you will get the power. So, that is the power of the signal. In similar way, one can also define power for the noise signal. Remember, noise is probabilistic, one has to take expected values and all that. Because noise is probabilistic, one has to take expected values, but nevertheless one can define a notion of a power for the noise as well. Now, the ratio of these two powers, okay, signal power divided by noise power, is defined as the signal to noise ratio. Okay. So, the signal to noise ratio has no units, power by power it cancels, there is no units. Okay. And typically signal to noise ratio is reported in dB scale. How do you convert any number to dB? You take logarithm to the base 10 and then multiply by 10. So, that is what you do to convert any number to dB. Let me give you a few numbers here. So, if the ratio, if SNR and you want to compare SNR in dB, maybe a few things can be looked at. SNR of 1, okay, actually corresponds to 0 in dB. Okay. SNR of 2 actually corresponds to roughly 3 dB. Okay. So, this is a calculation that you can do. You can add more values here, you put any other function here. So, remember this is actual SNR. Okay. You put 1 here, log 1 base 10 is 0. So, you get 0 dB. If you put 2 here, log 2 base 10 is around 0.3. So, you get 3 times, okay, and so on. Alright. So, you can put any other value here, you will get something in dB. Okay. This 2 to 3 is a good number to remember. SNR of 2 corresponds to 3 dB. Okay. So, it is one of those things to remember. Okay. So, SNR. So, what does SNR quantify? SNR, if SNR is high, then it means your signal level or signal power is higher than the noise power. Okay. So, your noise signal is significantly lower in amplitude and power and all that compared to your signal power. Signal power is very big, the noise power is very small when SNR is high. On the other hand, when SNR is low, 0 dB, if its SNR is 0 dB, then your signal power is equal to the noise power. Okay. So, when signal power and noise power are the same, you are likely to make many more errors, right. So, when as opposed to the case when the signal power is very large and the noise power is very small, you may not be making many errors. Okay. So, this is so SNR in some sense quantifies the signal, the quality of your channel, how good is your channel, okay, and that is very important to know, and all of our measurements and all that will be with respect to SNR. Okay. Now, the other very important measure in a digital communication system is error rate. Okay. Bit error rate is the next important metric, and that has a very simple definition. You transmitted A, okay, so this is the transmitted bit. This is the received bit. Okay. From the transmitted bit to the received bit, what is the error? Okay, probability that A does not equal A hat. Okay. So, now in a typical communication system, there is this Monte Carlo simulation method to estimate bit error rate. Okay, simulation method. Okay. There is also a theoretical method to compute this. I will talk about it soon enough, but for now let us understand what the simulation method will be. You actually transmit a large number of bits. Okay. So, tens of thousands of bits you transmit, and you know what bits were transmitted, you know what bits were received, okay, after this system, and then you compare, okay, and you see how many errors were made, and this ratio NE by N, as we know from our studies of probability, is a good estimate of the bit error rate. okay, the probability that A is not equal to A hat, a good estimate is this. Okay. So, this is the way in which things are captured. Okay. So, as you can imagine, as SNR increases, your bit error rate is going to fall. Okay. So, this is the essential trade off in digital communication systems. How is bit error rate related to SNR? How does bit error rate vary with respect to SNR? Okay. So, one can do also a nice and simple theoretical calculation for this, but before that I want to spend a little bit of time in talking about this SNR in continuous time and discrete time very quickly, just to convince you how this works. Okay. So, let us look at the continuous time channel in which the signal power is P and the noise power spectral density, okay, is N naught by 2. So, this is in the spectral domain, you think of N naught by 2 as the noise power spectral density, and let us say you are using a bandwidth of 2W, okay, some number 2W hertz of bandwidth. Now, if you look at the noise power, okay, noise power, signal power was P, noise power is actually power spectral density times the bandwidth. So, you get N naught times W. Okay. So, in the continuous time domain, the SNR becomes P by N naught W. Okay. So, this is the main calculation here. So, it is a very simple calculation for the signal to noise ratio in the continuous time domain. Now, how do you get this noise power spectral density? In an actual physical system, there are devices that will tell you what the PSD is, okay, and many scopes and other devices have ways of measuring this noise power spectral density. So, you can get N naught by 2 and you know what bandwidth you will be using. So, you can compute this quantity. So, all these quantities are perfectly computable in a physical system. Okay. Now, if you are using a bandwidth of 2W, it turns out there is this Nyquist rate of transmission in the channel. You can send for one symbol, the time that you can spend for it is 1 by 2W, okay, or another way to put it is the symbol rate is 2W, okay, 2W symbols per second you can send without any interference, etc., etc. Okay. So, the time that you have in one symbol is 1 by 2W. Okay. So, for the power is P and the time for which you can send that one symbol, the signal that you can send is 1 by 2W. These are rough estimates, but this is pretty good. Okay. So, when you convert from continuous time to discrete time, one does not think of power, one thinks of energy. Okay. So, energy, because you are sending a certain signal for a particular time, the total accumulated energy corresponding to that the signal that you sent is a good measure of the energy you expended for transmitting that particular bit. Okay. So, now energy is power into time. Okay. Power was P, the time was 1 by 2W. So, this is energy per symbol. Okay. So, this is a this comes from energy equals power into time. Okay. So, now how does the noise get converted into discrete time? Okay. So, this requires a little bit of calculation. Okay. I am not going to go through that, there is lots of theory behind it. So, it turns out when you convert noise from continuous time, whatever continuous time model you might have, to discrete time, the noise energy is simply the variance of the noise, and that is simply the level of the noise PSD, okay, N naught by 2. So, this is how noise converts from continuous to discrete time. Okay. So, the variance or energy in the noise is simply sigma squared, and the energy in the symbol is P times T is P by 2W. Okay. So, the main moral of the story is, if you take ES by sigma squared in the discrete time domain, that exactly equals P by N naught W in the continuous time domain. Okay. So, the main story in this slide is you do not have to worry about the continuous time situation at all. Okay. You only worry about the energy in the symbol and the noise variance in the discrete time domain, and your SNR in discrete time you define it as ES by sigma squared, energy in the symbol divided by sigma squared, and you are fine. Okay. So, that is completely enough. Okay. So, keeping this in mind, we will never ever go back to the continuous time domain again. We will only be in the discrete time domain, and we will be happy with the calculation of the SNR in the discrete time. Okay. So, let us see how to calculate SNR for a particular modulation scheme. The modulation scheme that we will use is BPSK. So, it turns out the signal energy is mean of the square of the symbols, okay, mean of the square of the symbols, okay, and usually we will assume that the symbols are equally likely. Okay, equally likely meaning they are uniform, okay, +1 happens with probability half, -1 happens with probability half. So, how do you compute the signal energy? You square +1, you square -1, right. So, this is one symbol +1, you squared it, and another symbol -1, you squared it, and then you divide by 2. So, this is the mean of the square of the symbol, so you get 1. Okay. In your BPSK model, this ES, the signal energy quantity, has this very simple expression which is 1, okay, and this is equivalent to the energy in the continuous time model. Okay, it is exactly the same. Of course, there will be some units and all that which will be different, but this one is a good model for that. Okay. And noise power is sigma squared. Okay. So, noise power, remember, in the discrete time domain, noise power, if you want to simulate and if you want to run it, it is just a Gaussian distribution. You can generate Gaussian noise of any variance. Okay. So, whatever variance you pick is the sigma squared. So, your SNR becomes 1 by sigma squared. Okay. So, that is the main story here. Okay. So, in the discrete time model, assuming BPSK, SNR is 1 by sigma squared. It is a very straightforward, simple calculation. Okay. So, now that we have SNR, how do we do bit error rate? Okay. So, for BPSK WGN, what is BER versus SNR? How do you compute bit error rate? Okay. So, here is a picture to show what happens. Okay. So, remember, we are going to use a threshold at 0. Okay. So, we are using a threshold at 0. Okay. And if you transmit a +1, right, you are going to say the received value, if it is positive, I will not make any error. On the other hand, if you transmit a +1 and the received value becomes negative, you will make an error. So, that is what is this situation here. Okay, you transmitted a +1, but the noise was so high on the negative direction that it pushed you over the threshold, it became less than -1. So, you made an error. Okay. And here is the other situation, when you transmitted a -1, but you made an error because noise was very high, it became greater than 1. So, it pushed you to the right of 0. Okay. So, like I described, the probability of error, the bit error rate expression has two parts to it, the sum of two parts. The first part is the probability that S equals +1 and then the noise is very high and negative, so that you make an error. The second part is probability that S is -1 and then the noise is very high and positive and you make an error. Okay. Now, the first part in this probability is easy, probability that S equals +1 is half, probability that S equals -1 is half, that is easy. Now, what about this guy? Probability that n is less than -1. Okay. So, now to compute this, one needs the PDF of the noise. Okay. The noise is Gaussian distributed. So, the PDF is like this. Okay. The noise is Gaussian and the PDF of noise has this formula 1 by √2 pi sigma e power minus x squared by 2 sigma squared, that is the formula. And if you actually plot it, you will have some fall like this. Okay, it will look like that, it will never quite go to 0, but it will go very close to 0. Okay. So, 0 and then you have +1 here, let us say, and -1 here, let us say. Okay, it will be symmetric, I have not drawn it quite symmetrically, but it will be symmetric. Okay. Now, what is this probability that n is greater than +1 or less than -1? It is this area. Okay, this area is the probability that n is less than -1, and this area, which maybe I should redraw this, let me just say this. Okay, let me redraw this. So, it should be +1 somewhere here, and this area out here is the probability that n is greater than +1. Okay. Now, those areas can be represented in terms of the Q function. Okay, this Q function is defined here. I will not go into details here. The Q function is available in most platforms, computing platforms, you can use it. So, if you write it down carefully, you will see that these two probabilities are actually equal to Q of 1 by sigma, and this is also equal to Q of 1 by sigma. Okay. So, once you write that down, this is Q of 1 by sigma, this is also Q of 1 by sigma. So, if you multiply by half and add it up, you will simply get that the overall BER is Q of 1 by sigma. Now, if you remember, SNR is 1 by sigma squared. So, what is 1 by sigma? Square root of SNR. Okay. So, the probability of error, bit error rate, is nothing but Q of square root of SNR. Okay. So, this is a very classic formula for BPSK AWG, and I just quickly showed you a derivation for how it works. So, this is bit error rate versus SNR in BPSK AWGN. So, this is a very nice complete theoretical calculation.